let's get started again. So before the break, we derived the Hamilton Jacobi equation. And this S, which is now just the second class of generating functions, depends on the old set of coordinates and the new set of canonical momenta, which are constants due to the equations of motion. So basically, this is the first order partial differential equations for n plus 1 variables. And these n plus 1 variables are the n spatial coordinates and time. This S is conventionally in the literature dubbed to Hamilton's principal function. So what I would like to do now is to go through how we can use this equation to solve the system. So when I say solve the system, what do I mean? Or put differently, what do we need to find to know how the system behaves? Which quantities do we need to determine? Those are the equations we use. But which quantities do we want to obtain?
We need one constant of motion for each variable.
So that's right, that's the mean we use. But what is the result that we're after? Which quantity do we want to sit left with? What is it in this equation that we want to determine? So say you have a mechanical system and someone asks you to solve for this system. What is it they ask? What is it in reality they are asking you to find? It's the time dependence of the coordinates, right? If we know how the q's and the p's behave with time, then we know everything about the system. So what we need to find from this equation is a solution for q and p. And in the same way, using the Lagrangian method, for instance, what we're interested in ultimately is a solution for the generalized coordinates, q and q dot. So when you're asked to solve for the system, the idea is that you're supposed to find the time dependence of the generalized coordinates and or momentum. So I just wanted to emphasize this because in this equation we have a lot of variables. We have this S, for instance. So one could speculate, okay, what we need to solve the system is to find S. S is just a tool that we use to find the Q's. So it's important to keep in mind what we're after ultimately. So the aim is to determine the time dependence of the coordinates and the momenta. That's what we mean by solving the system. Now, we're dealing with extremely simple equations of motions, at least in terms of the new coordinates, because the new coordinates are just constants. So we know, for instance, the canonical moment of large P may be set to some constants alpha I. So Hamilton's principal function depends on the coordinates and all of these constants, which are basically initial conditions in our problem. There are integrational constants that appear, and time. Now, the key to obtaining the time dependence of Q and P is to use the defining equations of transformation for F2, the second class of generating functions, on this function here, because this is F2. And the defining equations for the canonical transformation for F2 look like this. So in our case, where the large Q and the large P are constants, these defining equations take the following form. So we see here that what I've done is to replace large P with the integrational constants alpha, since large P is a constant. And I've also defined that large Q here, which in general is equal to this, in our particular case also is a constant due to the equations of motion. So when I write Q alpha T here, Q represents all the Q, Q1, Q2, etc. And at this point, we can start to solve for the actual coordinates and the momenta. So using, for instance, equation 1, s is a known function. It depends on small q, the integrational constants, and time. So we take this known function and we derive it with respect to these alphas. Having done so, we obtain some equation. Now we take this equation and invert it so that we express it as qi is a function of alpha, beta, and t. So originally we started with this. So we just rewrite this equation to the following form. So once you solve one, you can rewrite it, just rearranging the terms to find qi as a function of time and these integrational constants. So that's half of our aim already accomplished. So now that we have qi in hand, we may insert it into 2 to find the momentum. And by then we have accomplished our full aim, namely to determine Q and P. So let me just point by point summarize the solution strategy using the Hamilton Jacobi equation. The first step is to just construct the Hamilton Jacobi equation from the known Hamiltonian. So we assume that the Hamiltonian is given. We need that to describe a system. Using this equation, which is a first-order differential, partial differential equation for S, solve for S, which will be a function of Q, alpha, the integrational constants, and time. second step was to obtain Hamilton's principal function. The third step is to, having now obtained S, calculate large Qi, which is a constant, which we know from the equations of motion, calculated by taking the partial derivative of S with respect to alpha, and then rearrange the resulting equation you have in order to isolate Qi, so that you find Q as a function of only integrational constants and time, meaning you have now established the time dependence of Q. Yep.
Is it obvious that it's possible to rearrange the equation to isolate the Qi's? Doesn't it depend on some partial derivatives being non-zero?
You're right. So we're basically assuming here that you can rearrange the equation. It's invertible.
Is it always invertible?
No.
Where you cannot?
I'm sure there are cases where you can't. So, I mean, it's possible to end up with something really nasty, that you have some constant here equal to some very complicated function of Q, so that you cannot isolate Q from this equation. But, yeah, so that would be a special case. But if it's possible, then it should be doable like this. Yeah. So we're assuming here that you can invert this equation. And if you cannot, well, then the problem is most likely too complicated to solve analytically anyway. So you would have to do it numerically. All right. So that's the third step. And the final step, having now obtained Qi, is to calculate the original momentum. And that's basically the general strategy that you may follow while using Hamilton Jacobi theory. So you find S, you find Q, and you find P. So the hardest part of this strategy is basically the initial step to solve for S. Once you have S, it's a matter of doing some algebraic manipulations and doing derivation. Now, the treatment that we've been doing so far have been quite general in the sense that we have taken into account a possible time dependence of the Hamiltonian. So we'll consider here briefly the special case where there is no time dependence in the Hamiltonian, and in that case, this simplifies. So if H has no explicit time dependence, meaning that we have a conservative system, then we may write Hamilton's principal function in the following way. So we can basically separate Hamilton's principal function into a time-independent and a time-dependent part. And this is not possible to do for the general case where the Hamiltonian is time dependent. So let's see what happens if we do this. So we start out by the first step in our general solution strategy, namely to consider the Hamilton Jacobi equation. And we now insert our ansatz for S, giving us this. Now, W has no dependence, explicit time dependence on time. So this is 0. And in effect, the Hamilton Jacobi equation gives us that H is equal to A, where A is some constant. Now the question is, can we say something about what this constant is? Or is it just arbitrary? So we have a time independent. There's no explicit time dependence, meaning that we have a conservative system. So H is apparently some constant. Yep, the energy. So for a conservative system, the Hamiltonian is just a constant and is given by the energy. So A is in fact the energy in disguise. So the conclusion here is the following. So the Hamilton Jacobi equation for a conservative system takes the following form, since the Hamiltonian is simply the energy. And moreover, the canonical momenta in the new set of coordinates, in other words, these integrational constants, can be obtained from this W, since that's the only term which can give a contribution. This W also has a name. It's known as Hamilton's characteristic function. Now, it's not the end of the world if you get these terms mixed up, which one is the characteristic, which one is the principal function. So, but it's good to be aware of the notation here. So S is the principal function, W is the characteristic function. Okay, so let's have a look at how this theory works. Let's have a look at it in action. And although it's maybe a pretty boring example by now, I'd like to use again the harmonic oscillator for the following reason. I believe it can be instructive to consider the same problem using many different approaches. But I do believe there's an exercise, one of the final exercises posted on the web, where you treat a different problem using the same theory. So, standard form for the Hamiltonian, considering one dimension for simplicity, just to show the principle of how it works. All right, so we know that P is equal to ds dq. So the first step was to construct the Hamilton Jacobi equation, and we have to do that by substituting in place of the original momenta. We have to substitute this partial derivative. So we get this equation here. All right, now the task is to solve for S. Are there any simplifications we can do here?
We can replace the SDT by the energy.
Yep. So we can write this as E plus ds dt equals 0. And the reason for this is that we're dealing with a conservative system. There's no explicit time dependence in the Hamiltonian. Now, since it's a conservative system, we know that S can be written as, the principal function S can be written as the characteristic function W minus energy multiplied with time. So this last partial derivative term here is simply minus the energy. So we have this equation now. And in fact, what I can do here is to erase the S and replace it with a W. Because only the W has a Q dependence in S. Okay, looks a little bit better. We still have to solve for S, which amounts to solving for W, since it's given like this. So we have to solve this equation for W. W is a function of Q and a set of integrational constants. So we should be able to isolate W here and then integrate, or we should be able to isolate the partial derivative here and then integrate it over Q to find W, and then some integrational constant. So by moving some terms around a little bit and performing an integration of the Q, we find that W is given like this. So by then we have now accomplished the second step of our general solution strategy, namely we have identified S. Now the next step is to start computing the partial derivatives of S in order to identify Q and P. So we have, for instance, this relation, and I've attached a prime here because I'm later going to absorb a constant into this term, just to simplify notation. But this is just a constant. So we're using here, this is this corresponds to the following equation for the second generating function. And we know this is a constant, and I'm just naming this constant beta prime. So taking S and deriving it with respect to alpha, we obtain this. Now you may wonder what happened to this term, because we had the energy here, right? So it seems like I've treated the energy as an alpha here. So what I've done in essence is just to say that, okay, I'm choosing my integrational constants to be equal to the energy. We have one integrational constant in this case, since it's 1D. So I'm just choosing it so that it's equal to the energy, meaning that we get this equation. So I'm exploiting the freedom I have in these constants. So this integral can be solved literally, and the solution looks like this. So it's a standard integral you can look up. So now we have written down this equation. So now we have to check, is it possible, is this equation sufficiently well behaved that we can actually invert it to isolate Q? And in fact it is. We'll just multiply, we'll take this constant over here, put a sign on both sides. So what we get is that Q is some prefactor multiplied with sine omega t plus this integrational constant here, beta. So this beta here now is beta prime multiplied with omega. So that's why I used the prime initially. And omega is given as k over m. It's this term inverse. Now keep in mind that alpha is the energy. So if you consider the derivation we performed using the canonical transformation a couple of lectures ago, this is identical. So we get exactly the same solution for Q. Okay, we'll finish this example next time.